In order to ensure that our rocket remains stable during flight, we decided to utilize large trapezoidal fins to minimize rotation. To ensure that the rocket does not flip, the center of pressure needs to be below the center of gravity. We wrote a MATLAB script to estimate the center of pressure from our rocket dimensions and loaded mass into the nose cone to ensure that the center of gravity is above the center of pressure. This fact allows us to approximate the rocket as a particle and use double integration of the acceleration equation to calculate the trajectory. First, we conducted a force balance with the total forces equal to the thrust, which decreases over time, plus the air resistance, which depends upon the square velocity, plus the force of gravity, which decreases as the mass of water inside decreases. Once the water is spent, the only forces are air resistance and gravity as it glides. To simplify our model, we decided to keep constant the amount of water in the rocket, which is 420 milliliters, and instead focus on adjusting the pressure and launch angle. We generated a trajectory for several combinations of pressure and launch angle and tested it through experimentation. We believe the largest uncertainty lies in the drag coefficient of our rocket, so we adjusted that value as we tested to refine our trajectory calculations. Here we have the results of our efforts with a final trajectory model based off both our theoretical calculations and our experimental testing.
In this lab, we were tasked with constructing a rocket made out of a 2-liter bottle, water, and pumped air. We then used principles from dynamics, thermodynamics, and aerodynamics to project the trajectory of the rocket that would occur as we varied different independent variables such as amount of water, air pressure, and angle of launch. To achieve a range of motion, there must be a thrust force. We derived a formula to project the thrust force of our rocket based upon atmospheric pressure, gauge pressure, density of water, and cross-sectional area of the nozzle. To derive this formula, we began with Newton's second law and an analysis of momentum. For the first step, we related the thrust force of the exit velocity expelled water by stating that the rate that mass leaves the rocket is the same as the velocity of water at the exit. Then, we wrote out an expression of the mass flow rate of water, relating density, volume, and cross-sectional area of the nozzle. We substituted Bernoulli's equation for the velocity of the water. Finally, we related gauge pressure to atmospheric pressure, substituted into Bernoulli's equation, and plugged all of this into the equation for thrust. This was the first in our system of equations. Second, we found a relationship between pressure of the rocket and volume of air. We first related the pressure and volume of the initial and final states of an adiabatic process with adiabatic constant K equal to 1.4. We then wrote an expression of the change of volume of air in the bottle over time, assuming that the volume of air inside the rocket changes during the launch. Thus, we were able to express the volume of air as a function of time. Third, we explained the relationship between initial and final volumes of air and the atmospheric pressure, assuming a polytropic process. We used the ideal gas law between states A and B and solved for P. Combining our three equations, we found an expression for thrust force that we then used to help us determine the trajectory of the rocket.
On our first test day, our rocket did not launch because there was a hole in the bottle, so the air couldn't pressurize. There were no bottles left in lab to fix our rocket, so we had to test on another day. On the second day, we were given a target of 70 feet. Based on our MATLAB script from earlier, we put our rocket at 60 degrees from the horizontal and filled it to 40 psi gauge. On the first trial, our rocket landed 32 feet to the right of the target. It moved to the right immediately after leaving the stand, but flew straight afterward. So on the next trial, we tilted the pad to the left. Our rocket launched straight and landed on the target because Paul caught it while standing on the target. However, the nose fell off and landed about 11 feet behind the target. Our rocket landed around 10 feet away from the target. This means that our navigation and thrust calculations had a 15% error. As you can see in the videos, the rocket launched fairly straight, so our center of pressure calculation was good too. The fins were designed to be heavy so that they wouldn't deform in the air. We used MDF instead of cardboard like most groups. The fins were also large, around 2/3 the length of the rocket, to add some extra weight to it. We wanted to make our rocket on the heavier side to increase the stability for the rather short flight. Our fins had a hole in the middle with the goal of making them slightly lighter. We had to make them lighter because the center of pressure was only 1 inch below the center of gravity. We wanted the center of pressure to be about 3 inches below the center of gravity in order to increase the stability. However, having fins that weren't completely solid caused our rockets to move in one direction immediately after being launched because the air moved through the fins until the rocket was stabilized. This, as well as the launch pad not being pinned down completely, caused our rocket to gear toward the right, just right after launch. This could have been avoided by adding more weight to the nose and making the fins solid. Other than that, our rocket performed as expected.